I can't find another proof for our gravitational field energy equation. The ones that are out there, you can Google them, but they all come back to basically a calculus proof, which is a little bit beyond us mathematically. I'm going to do it now. I'll talk you through it. You can YouTube it and find other versions of it, but everyone that I found is calculus. Later, when you learn calculus, especially after derivatives, then this will make more sense. So if nothing else, watch it now, see if you can follow along, and then file this away that later, after derivatives, maybe rewatch this, and it'll make more sense. The physics really is very short in this. The physics is, when we've got a changing force, I don't want that. Let's try this again. When our force is in constant, then the energy generated by that force is the area under the force versus distance curve. We didn't use this in grade 11. We didn't need to. Our force was always constant, so we just got work was FD, and then we could work off of that or come up with other equations from that. For gravity, though, our gravity equation is Fg is gmm over r squared. So in our force versus distance curve, really, in our force versus distance curve, instead of d, we're going to call it r. If we were to graph it, so think to your math class, we've got a 1 over x squared thing. It is going to be a graph that's definitely not linear. If this is r and this is f, then it's going to be swooping downhill like that. If I can figure out the area under that curve, that'll tell me the energy stored in the system. That's just a weird physics property. And then to do it, we actually need to find calculus. To find the area under a regular curve, I could just break it into geometric shapes. So the calculus is kind of based off of that. If we take a little sliver down here, that is almost a trapezoid. It's got a particular width, and it's got a particular height based on the value of the function at that point. So really, to find the area under the whole curve, what calculus said is let's find the area of that sliver. It's going to be f multiplied by the width of that little sliver. In calculus notation, we call the width of that sliver dr, just a variation of delta r. If we can find that area, the width of dr multiplied by the height of f, and then sum up all the other little slivers that would be here, the sliver here, dot, dot, dot that way, dot, dot, dot that way. If we sum up those slivers, that'll give us the area under the curve. So in words, the gravitational energy is the area under the FG curve. In calculus, I want to find the sum of the height, which is going to be a value of the function, multiplied by the width, which they gave this cool thing of dr, and I'm going to sum those up. The sigma sign for summation, instead of the goofy S, we do a swooping capital S. That's just a notation for summing, which you're going to learn is the integral sign. So next line, EG is the integral. F is the value of the function. The function's following gmm over r squared, dr for the slice that we're looking at. It's a calculus thing that you'll get to, so you're going to have to trust me. Gm and m are constants, so they don't factor into the integration. So we get something like this. You could Google that, or you could look it up, but when what we're doing here is called an integral. It's the opposite of a derivative. Derivative. Once you've learned derivatives in calculus class, then you would be able to do this. It might help if we write that a little bit differently. Gmm integral instead of 1 over r squared. Sometimes people see it better if I make it r to the negative 2. dr. An integral is just a riddle. What function, when I start with it, after doing the derivative, is my answer r to the negative 2? It's kind of like squaring and square roots are opposites. We all know that 5 squared is 25. But as a riddle, I could say, what number, when I square it, when I'm done squaring, do I get 25? You could work backwards and say the answer is 5. What function, when I'm done doing a derivative, is my answer r to the negative 2? In math class, just the way things are in math class, you're going to always use x's and y's. So maybe if you've done derivatives, it would be something like what function, when you're done the derivative, is the answer of your derivative x to the negative 2? Once you've done derivatives, you'll see that that's actually not a hard riddle. The answer is, and this is where you're going to have to trust me, the answer is negative r to the negative 1. That's the answer to the integral. By writing down negative r to the negative 1, that gets rid of that summation sign, that gets rid of the dr, that is the sum of all those little slivers. We're going to rewrite that a little bit differently. We're going to say that EG is, we've got a negative GMM over R. That is going to be our new equation for gravitational field energy. Sometimes it's called gravitational potential energy. Sometimes it's called universal gravitational potential energy because it's connected to the universal gravity force. That's what we'll use moving forward. If you read the document and read through all my crazy scenarios, the negative shouldn't surprise you. Keep working through the document. We'll plug and chug and figure out how this thing works. You don't need to have the proof memorized by any means, but hopefully after you learn calculus, if you come back and look at it, you'll see that this actually does kind of make sense.